Welcome to this problem walkthrough. Today, we'll be tackling the night dialer problem, an intriguing challenge that combines dynamic programming with the unique movement rules of a chess knight. Stick around to discover how to calculate all possible phone numbers of a given length using this fascinating approach. In this problem, we are tasked with simulating the movement of a chess knight on a phone keypad to generate distinct phone numbers. A knight moves in an L shape, which means two squares in one direction and one square perpendicular to it, or one square in one direction and two squares perpendicular to it. Only valid moves that stay within the boundaries of the keypad are allowed. The keypad is laid out like this: the digits 1 through 9 are in a grid, and the digit 0 is below 8 in the middle of the bottom row. Given an integer n, our goal is to calculate the total number of unique phone numbers of length n that can be dialed, starting from any digit on the keypad. Since this number can grow very large, we will return the result modulo 10 to the power of 9 plus 7. For input, we are given a single integer n, which represents the desired length of the phone number. The constraint on n is that it can range from 1 to 5,000. The output for this problem is a single integer representing the total number of distinct phone numbers of length n, modulo 10 to the power of 9 plus 7. Let's consider an example to understand this better. If n equals 1, the output is 10. This is because, with a phone number of length 1, the possible numbers are simply the digits 0 through 9. Since there are exactly 10 digits on the keypad, the distinct count of phone numbers is also 10. Now, let's look at another example where n equals 2. In this case, the knight starts at any digit on the keypad and makes exactly one move to a valid new position. The number of valid moves differs depending on the starting digit. For example, starting from 1, the knight can move to either 6 or 8. From 2, the possible destinations are 7 and 9. Similarly, from 3, the knight can move to 4 or 8. The digit 4 has 3 valid moves, which are 3, 9, and 0. However, digit 5 stands out because it has no valid moves at all. When we sum up all the valid moves across all digits, we find that there are 20 distinct phone numbers of length 2. To complete the explanation for n equals 2, let's review the valid moves for the remaining digits. Starting from 6, the knight can move to 1, 7, or 0. From 7, the valid moves are 2 and 6. From 8, the knight can move to 1 or 3, and from 9, the valid moves are 2 and 4. Finally, starting from 0, the knight can move to 4 or 6. On average, each starting digit leads to about 2 valid moves, which results in a total of 20 distinct phone numbers of length 2. Now, let's consider a slightly longer phone number, where n equals 3. In this case, we calculate the number of valid sequences by considering every possible chain of moves, starting from each digit and extending to a length of 3. For n equals 3, the total number of distinct phone numbers is calculated by summing up all possible sequences of length 3 starting from each digit. This involves recursively determining all valid moves and extending the sequences step by step. The result is 46 distinct numbers. Keep in mind that the computation grows significantly as n increases, which is why we need to use an efficient approach like dynamic programming to solve the problem for larger values of n. To summarize, the constraints remind us that n can go up to 5,000, and the knight must always stay within the bounds of the keypad. The result must also be returned modulo 10 to the power of 9 plus 7 to handle the large numbers involved. Some important edge cases include n equals 1, where the output is always 10, and n equals 2, where the knight's limited moves determine the count. For larger values of n, optimization is key to avoid excessive computation. The night dialer problem revolves around determining how many distinct sequences of length n can be formed on a phone keypad when moving like a knight in chess. The knight starts at any digit and moves in an L shape, which means jumping 2 squares in one direction and 1 square in a perpendicular direction. On a standard keypad, this creates up to 8 potential moves, although some moves will lead out of bounds, depending on the starting digit. For example, starting at digit 1, the knight can only move to 6 or 8. The ultimate goal is to compute the total number of valid sequences modulo 10⁻9 plus 7. To solve this, we can explore several approaches. One idea is the brute force method of recursive backtracking, where we simulate every possible sequence of moves, starting from each digit. While intuitive, this approach has significant limitations due to its exponential complexity, as each of the n moves can branch into up to 8 new moves. This makes it infeasible for large values of n due to redundant calculations and rapidly growing computational requirements. In the brute force approach, we simulate the knight's moves recursively for each digit, decrementing n with every step and stopping when n reaches 0. However, this method involves a large number of redundant calculations. For instance, sequences starting at digit 1 with a specific length are repeatedly recomputed. To address these inefficiencies, we can turn to dynamic programming, specifically a tabulation-based approach. Here, the idea is to iteratively compute the number of valid sequences for each digit and sequence length in a bottom-up manner. We define dp, I, j, as the number of sequences starting at digit I with length j. Using a predefined adjacency list to represent valid knight moves, we can transition between states by summing up the results from all digits that can move to I. The recurrence relation for this is straightforward: dp, I, j equals sum dp, k, j1, for all valid k that can move to I. The base case is simple: dp, I, 1 equals 1, because there's only one sequence of length 1 for any starting digit. This approach drastically reduces redundant calculations, resulting in a time complexity of O, n asterisk 10 by 8, and a space complexity of O, n asterisk 10, where 10 is the number of digits and 8 is the maximum number of moves per digit. Although tabulation-based dynamic programming is efficient in terms of time, it still requires significant memory to store the dp table for all sequence lengths. To optimize space usage, we can observe that to compute the sequences for length j, we only need the results from length j1. This means we can replace the full dp table with two arrays, previous, representing the results from length j1, and cur, representing the results for length j. This space-optimized version retains the same time complexity of O, n asterisk 10 by 8, but reduces the space complexity to O, 10, as we only store the results for the current and previous sequence lengths. While this approach is more memory efficient, it achieves the same level of time efficiency as the tabulation method. Additionally, another advanced technique called matrix exponentiation can be applied to this problem. By representing the keypad as a graph where digits are nodes and valid knight moves are edges, we can compute the total number of sequences using matrix exponentiation on the adjacency matrix of the graph. This method has a time complexity of O, 10 cubed asterisk log n, and a space complexity of O, 10 squared, making it faster for very large n. However, matrix exponentiation is less intuitive and harder to implement when compared to dynamic programming. Each of the approaches discussed comes with trade-offs. The brute force method is easy to understand but computationally prohibitive for larger values of n. The tabulation-based dynamic programming approach is efficient in terms of time but uses more memory than necessary. The space-optimized dynamic programming method strikes a balance between time and space efficiency, making it well-suited for this problem. While matrix exponentiation is the fastest for very large n, its complexity and implementation overhead make it less practical for typical constraints. Ultimately, the space-optimized dynamic programming approach is chosen for its clarity, efficiency, and suitability given the problem constraints. It avoids redundant calculations, minimizes memory usage, and handles modular arithmetic seamlessly, making it a robust and practical solution. Key insights include recognizing that the number of sequences depends only on the previous state, pre-computing knight moves for efficient transitions, and using modular arithmetic to manage large outputs without overflow. To solve the knight dialer problem efficiently, we use dynamic programming. The first step is to understand how the knight moves on the keypad. The knight moves in an L shape, meaning it takes 2 steps in one direction and then 1 step perpendicular to it. For example, starting from the digit 1, the knight can jump to digits 6 and 8. Similarly, each digit on the keypad has specific destinations the knight can move to. To represent this, we create a mapping where each digit is a key, and its value is a list of possible destinations. For instance, the digit 0 has valid moves to 4 and 6, while 5 is unreachable because no knight move lands on it. This mapping serves as the foundation for determining the valid transitions between digits as we construct phone numbers of increasing lengths. Now that we understand the knight's moves, we define the problem's input and output. The input is n, the desired length of the phone number, and the output is the total number of distinct phone numbers of length n that can be dialed starting from any digit. To solve this, we define a dynamic programming state, dp(i)j, where dp(i)j represents the number of distinct phone numbers of length I that end on digit j. For the base case, if the phone number length is 1, there is exactly one way to end on any digit, so dp1j equals 1 for all digits. Next, we define a recursive transition. To compute dp(i)j, we sum up all the ways to reach digit j from its neighbors in the previous step. Specifically, dp(i)j equals sum dp(i1) neighbor for neighbor in moves j. Using this transition, we can iteratively calculate the values of dp for all lengths from 1 to n and all digits from 0 to 9. To optimize the space complexity of our solution, we note that at any step, we only need the current row and the previous row of the dp table. Instead of maintaining a full 2D table, we use two arrays, previous to store the values of dp, i1, and cur for dp, I. These arrays alternate between iterations, reducing the space complexity from n*10 to 10 by 2, which is effectively constant space relative to n. After computing all the values up to length n, the final result is obtained by summing up all the values in dp, n, or equivalently, in the previous array after the last iteration. It's important to handle edge cases as well. For instance, if n is 1, the result is always 10, since any single digit is valid. Additionally, ensuring the move mappings are accurate, especially for digits like 0 and 5, is critical to the correctness of the solution. The keypad and the knight's moves can be thought of as forming an implicit graph. In this graph, each digit is a node, and the valid knight moves define the edges between nodes. This graph-based perspective helps us understand how the problem is fundamentally about counting paths of length n in this graph. Since the result can grow very large, we apply a modulo operation, specifically 10⁻9 plus 7, at each step to prevent integer overflow. The algorithm relies on a few key data structures. A dictionary is used to store the valid moves for each digit, allowing for efficient neighbor lookups. Arrays, previous and cur, are used to track the number of phone numbers ending at each digit for consecutive lengths, offering fast access and updates. As for complexity, the time complexity is n*10*k, where n is the phone number length, 10 is the number of digits, and k is the maximum number of neighbors for any digit. Since k is at most 3, this simplifies to n*10. The space complexity is 10 by 2, thanks to the use of two arrays, making it efficient both in time and space. Here, we start by defining the knight dialer function within our solution class. The first thing we do is define a constant mod set to 10 to the power of 9 plus 7. This ensures that our results remain within the bounds of integer arithmetic by taking modulo at each step. Next, we define a dictionary called moves that maps each digit on the keypad to its possible moves according to the knight's movement pattern. For example, the knight can move to digits 4 and 6 from 0, or to digits 6 and 8 from 1. The key value pairs comprehensively list all these valid transitions. Following that, we initialize a dynamic programming table dp as a 2D list. Here, dp(i)j represents the number of distinct ways to reach digit j in exactly I moves. Initially, the table is filled with zeros. To handle the base case, we know that for the first move, there is exactly one way to start at any given digit. So, we set dp0j to 1 for all digits j from 0 to 9. Finally, we use a nested loop to begin populating the dp table for subsequent moves, starting from the second move onward, with I iterating from 1 to n1. Now, for each move I, we iterate over all the digits j on the keypad. For each digit, we look at its possible previous positions using the moves dictionary. For each of these previous positions, we add the value from the previous row in the dp table to the current cell, representing how many ways we can reach digit j in move I. Since we're working under modular arithmetic, we take modulo mod at each step to prevent overflow. Finally, after populating the entire dp table, we calculate the total number of distinct sequences that end on any digit after exactly n moves. This is done by summing up all the values in the last row of the dp table, dp, n1, and then taking modulo mod one last time to ensure the result remains within bounds. The function then returns this final result, which represents the total number of valid sequences the knight can generate on the keypad with n moves. Here, we are implementing the knight dialer problem in Java. To start, we define a constant mod with the value 1,000,007 to handle the large numbers we'll encounter due to modular arithmetic. Next, we create a 2D array named moves to map each digit on the keypad to its possible next moves based on the knight's movement in chess. For example, from the digit 0, the knight can move to digits 4 and 6, while from digit 4, it can move to 3, 9, and 0. This array essentially encodes the rules of movement for the knight. Then, we initialize a 2D dynamic programming table, dp, where dp, I, j, represents the number of distinct ways to reach the digit j after I moves. To set up the base case, we populate the first row of the table using arrays.fill, dp, 0, 1, indicating that there is exactly one way to start at each digit with one move. Now, we calculate the values for the subsequent rows of the dp table. Using a nested loop, we iterate through each move I and each digit j. For each combination, we initialize dp, I, j, to 0 and then sum up the contributions from all the valid previous positions, which are defined in the moves array. This ensures that for each digit j, we correctly compute the total number of ways to reach it after I moves, applying the modulo operation to keep the results manageable. Finally, we calculate the total number of distinct sequences that can end on any digit after n moves. We do this by summing up all values in the last row of the dp table, again using modulo arithmetic. The result is then returned as the solution to the problem. This approach efficiently computes the answer using dynamic programming, ensuring we handle the constraints of the problem effectively. To solve the knight dialer problem, let's start with an example where the sequence length is n equals 2. Here, the goal is to determine how many distinct sequences of length 2 can be formed by a knight starting from any digit on a numeric keypad. We begin by setting up some initial variables. First, we define mod as 10 to the power of 9 plus 7 to ensure we handle large numbers efficiently. Next, we define a dictionary called moves that maps each digit to its valid knight moves based on the keypad layout. Then, we create a 2D table called dp, where dp, I, j, represents the number of ways to reach digit j after I moves. Initially, this table has all entries set to 0. For the base case, after one move, there is exactly one way to be at each digit, so dp, 0, is initialized to an array of all ones. This gives us a starting point to calculate the sequences for longer lengths. Now, let's compute the next set of values in the table for the second move. For each digit j, we calculate dp, 1, j, based on the possible previous digits the knight can move from. For example, if j equals 0, the knight could have come from digits 4 or 6. Using our base case values, dp, 1, 0, is calculated as dp, 0, 4, plus dp, 0, 6, which equals 1 plus 1, resulting in 2. Similarly, for j equals 1, the possible previous digits are 6 and 8, so dp, 1, 1, equals dp, 0, 6, plus dp, 0, 8, again resulting in 2. Repeating this process for all digits, we find that after the second move, dp, 1, becomes 2, 2, 2, 2, 3, 0, 3, 2, 2, 2. To get the total number of distinct sequences of length 2, we sum all elements in dp, 1, and take the result modulo mod. The sum is 20, which gives us the result for n equals 2. Next, we extend this approach to sequences of length n equals 3. The setup remains the same, with dp now being a 3 by 10 table initialized to 0. The base case is identical as well. After one move, dp, 0, is an array of all ones. For the second move, we calculate dp, 1, just like before, resulting in 2, 2, 2, 2, 3, 0, 3, 2, 2, 2. For the third move, we start computing dp, 2, j, for each digit j. For instance, when j equals 0, the knight could have come from digits 4 or 6. Using the values from dp, 1, dp, 2, 0, is calculated as dp, 1, 4, plus dp, 1, 6, which equals 3 plus 3, resulting in 6. Continuing with the third move, let's compute the value for dp, 2, 1. The knight can move to digit 1 from digits 6 and 8. Using the values from dp, 1, dp, 2, 1, becomes dp, 1, 6, plus dp, 1, 8, which equals 3 plus 2, giving us 5. Repeating this process for all digits, we arrive at dp, 2, equals 6, 5, 4, 5, 6, 0, 6, 4, 5, 4. To find the total number of distinct sequences of length 3, we sum all elements in dp, 2, and take the result modulo mod. The sum is 45, so the result for n equals 3 is 45. This demonstrates how the dynamic programming table grows as we increase the sequence length. Finally, let's consider the simplest case, where n equals 1. In this scenario, the knight does not move at all. This means that for each starting digit, there is exactly one sequence of length 1, just the digit itself. To find the total number of sequences, we sum up 1 for each digit from 0 to 9. This gives us a result of 10. This case serves as a useful base case for the problem and confirms that our solution works for any sequence length starting from the simplest scenario. To analyze the time complexity of our solution, we start by considering the initialization of the dp table. The table has dimensions of nx10, where n represents the number of moves and 10 corresponds to the digits on the keypad. Initializing this table involves iterating through all rows and columns, which takes n*10 time. This simplifies to O10n, and since constants are ignored in big O notation, this step contributes n time. Next, we look at the process of filling the dp table. For each move, from 1 through n1, we iterate over all 10 digits. For each digit, we examine its possible previous positions, as defined by the moves dictionary. A digit can have up to 3 possible moves, so the total work per move involves 10 digits and up to 3 operations per digit, making it 10 by 3, or simply 30, which is constant. Since there are n moves, the total time for filling the table is 30n, which simplifies to n. Finally, summing the last row of the table involves a quick iteration over 10 digits, which takes 10, or 1, time. When we combine all these steps, the dominant term comes from filling the dp table, giving the solution an overall time complexity of n. Turning to space complexity, the primary contributor is the dp table itself. With dimensions of nx10, the table requires storage for n*10 integers. Each integer takes constant space, so the table contributes 10n, which simplifies to n. Additionally, there is auxiliary space usage from the moves dictionary. This dictionary maps each digit to its possible moves and is fixed in size, as it only covers digits 0 through 9 with at most 3 moves per digit. Thus, the dictionary uses constant space, or 1. Other auxiliary variables, such as mod, I, j, and previous, also require constant space, contributing 1. When combined, the total space complexity is dominated by the dp table, resulting in n. To better understand the efficiency of our approach, let's compare it to a brute force solution. In a brute force approach, we simulate every possible sequence of knight moves. Starting from any digit, there are up to 3 choices for each move, resulting in 3 to the power of n possible sequences of length n. Accounting for all 10 starting digits, the time complexity becomes 10*3 to the power of n, which is exponential and highly inefficient for larger n. The space complexity in this case is n, due to the recursion stack if implemented recursively. In contrast, the optimized dp approach reduces the problem to iterating through n moves in 10 digits, with a constant number of operations per digit. This leads to a time complexity of n, and a space complexity of n, which are both significantly more efficient. Moreover, the dp solution performs uniformly across all inputs since it processes each digit and move in the same way. This means that the best, average, and worst cases all have a time complexity of n. The mathematical justification for the dp solution lies in its ability to exploit overlapping subproblems. For every digit and move, the number of valid sequences can be derived from previously computed results rather than recalculating everything from scratch. This reuse of results ensures that the total number of operations scales linearly with n. Additionally, the space complexity remains n, because we only need to store results for n moves, while the dictionary of possible moves is fixed in size and does not grow with input. Together, these factors ensure that the dp solution is both time and space efficient, making it the optimal approach for solving the knight dialer problem. When solving the knight dialer problem, there are several common mistakes to watch out for. First, it's crucial to ensure the knight's moves are accurately represented. For example, from digit 1, the only valid moves are to 6 and 8. Misrepresenting these connections can lead to incorrect results, so using an adjacency list or explicitly hardcoding the valid moves can help prevent errors. Another frequent issue is neglecting base cases, such as when n equals 1. In this scenario, all digits on the keypad are valid phone numbers of length 1, so make sure to handle these straightforward cases explicitly. Additionally, a naive recursive approach without memoization can quickly become computationally expensive, with exponential time complexity, making it impractical for larger values of n. To address this, it's essential to optimize using techniques like bottom-up dynamic programming or memoized recursion. Modular arithmetic is another area where mistakes often occur. Since the problem asks for results modulo 10 to the power of 9 plus 7, it's vital to apply the modulus at every step to avoid overflow errors. Lastly, some beginners overcomplicate the problem by trying to simulate the knight's movements on a physical chessboard. Instead, focus on the abstract graph representation of the keypad, which simplifies the logic significantly. Now, let's look at some insights that are particularly useful during interviews. Representing the keypad as a graph, with digits as nodes and valid knight moves as edges, can greatly simplify your logic and make the problem more intuitive to explain. When it comes to implementation, a top-down recursive approach with memoization is often easier to write initially. However, for interviews, a bottom-up dynamic programming approach is generally preferred because it's more efficient and avoids the pitfalls of recursion limits. Space optimization is another important consideration. Since only the previous state is required to compute the current state, you can use just 2 arrays of size 10 instead of maintaining a full dynamic programming table. This can be a great talking point in an interview. Additionally, recognizing key patterns like overlapping subproblems and optimal substructure is critical, as these are hallmarks of dynamic programming. To build further connections, consider related problems like LeetCode 70, climbing stairs, which also involves state transitions, or LeetCode 62, unique paths, which focuses on movement within a grid. Problems like these share similar principles and can help reinforce your understanding of dynamic programming approaches. Finally, let's explore some alternative approaches to solving this problem. A recursive solution with memoization is often easier to implement and understand, but it comes with a trade-off. While it simplifies the logic, it may be less space efficient and risks stack overflow for very deep recursions. On the other hand, a bottom-up dynamic programming approach is usually the preferred method because it avoids recursion limits and is more space efficient. It might be slightly more verbose, but the clarity and performance benefits make it worthwhile. Another advanced technique is matrix exponentiation, which allows you to solve recurrence relations in logarithmic time. This is highly efficient for large values of n but can be challenging to implement, so it requires a deeper understanding of linear algebra. Lastly, you might consider using graph-based breadth-first search, which is effective for exploring specific start digits or smaller values of n. However, BFS becomes inefficient when the goal is to compute all possible numbers for large n. Each of these approaches has its trade-offs, and the choice depends on the constraints and requirements of the problem you're solving. Great job following along. We've explored the Knight dialer problem, mastering dynamic programming and movement modeling. Take these insights to the next level by practicing similar problems, and stay tuned for more exciting challenges. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!